Okay, so we have our seminar today, and we are happy that today's speaker is Martina Lanini, and the title is Permutation, Representation, and Cohomology of Quiver Grassmannians, please.
Thank you very much. So thank you very much for the virtual invitation to Evgeny, Yevgen, and Igor. It's a pleasure to speak at your seminar. So what I'm going to talk about today is, well, joint work with Alex Twitz. So it's still ongoing. I hope that the main results I'm going to present today should appear on the archive in the next few weeks. Yeah, let's see. So the motivation of what we do is, well, it's more of a slogan maybe. So let me say, so the motivation is, so what we want to do is really to exploit geometry. Well, that's very vague, to construct representations, right? So that's a little bit really the core of what geometric representation theory is. And so let's say we all know here that that's a very rich interplay between geometry and representation theory, which may lead to, well, to very interesting results, meaning that the rich tools that geometry offers us can help us with understanding the algebraic phenomena and vice versa. So, well, today I want to focus on representations of a symmetric group or product of symmetric groups. And so the example I'm going to have in mind, I'm going to refer the whole talk long, is as an action on, so symmetric group action on the chromology of the variety of complete flags inside CN, but in fact, that's really the equivalent chromology.
I'm sorry.
Yeah.
Am I the only one that has this sort of gray rectangle in the corner of Martina's screen?
Same here.
Okay. So there's something covering your window on the right, bottom right. Probably another window.
Bottom right. I don't see that. Okay. So you see, so you don't see here.
Now it's better. Now you shifted to the right. Now it's okay.
Oh, I didn't touch anything. Okay.
Well, it's better now.
Mystery of Zoom. Okay.
Yeah, it's fixed.
So that's somehow the example motivated us, and I'm going to discuss it anyway into detail. So what we want to do today is somehow to upgrade this construction to some, well, I read something and I'm going to explain what this means. So that's an action of some product of symmetric groups. And this time the role of the flag variety is going to be played by the Grassmannian of quiver representation. Once again, we're going to look at some equivalent homology. So, well, that's a lot of things to be explained, even here. So I'm not really assuming that you know much. I decided since there's a lot of time, I'm going to start from the beginning. So, well, first of all, I'm going to say something about the varieties we're interested in. Okay. Then, of course, we have to, well, to make sense of a torus action. So I'm going to recall the classical setting and then tell you how you can extend this to the quiver setting. Well, then I wasn't sure how familiar you were with equivalent homology, so I'm going to spend time of it, but I decided I'm not going really to recall the definition, but rather a way of computing it, so that if you don't know the original definition, you just have an algebraic description. Well, then we are, of course, that's the core of the talk. We have to understand how these groups act on the two cohomology spaces. And then, well, at this point, we're going to have a representation of a symmetric group, or symmetric product of symmetric groups on a certain space. And then, so that's going to be 4. And then, of course, that's a natural question to say, how do we decompose it into reducible? So that's going to be the fifth part of this permutation representation. And here we are going to have, so to control the structure, we're going to require some properties of the underlying representation. And finally, depending on the time, I'm going to say something about action of a Neal-Heike ring on the cohomology space. Okay, so I'll try to follow my plan. So, well, the first section is about the varieties we have. Okay. Also, I think you've met this several times, so just let me set, the notation where I am. Sorry. I've lost, what happened? Yeah, sorry, I don't know why there are all these empty pages. So, okay, so here, I just want to introduce some notation. So FLN is going to be the variety of complete flags of subspaces of Cn. Okay, so here I have just nested subspaces where Vi is an element, so it's a nine-dimensional subspace of Cn. So that's a flag variety. It is a complex projective variety, while it's also a homogeneous space, and in particular is smooth. So it's particularly nicely behaved. Well, okay, that's the first character we want somehow to mimic. And so here, instead, we need, so we want to play with Quiver. So we just have an oriented graph. So Q0 is the set of vertices, Q1 is the set of arrows. And so we consider the category of complex representations of Q. So meaning we just have to pick a complex vector space. Well, I'll restrict to the finite dimensional setting. So one for any vertex. And then whenever we have an arrow A from I to J, well, we want to pick a linear map from MI to MJ, which we denote by MA. So that's a representation, so a collection of vector spaces and maps among them, which are arranged as the Quiver prescribes. So now let us fix some collection of non-negative numbers indexed by the vertices of the Quiver. Well, there is, well, first of all, let me say a set. So we pick all sub representations of M. So M is a representation as above, and a sub representation here is nothing but a collection of, again, vector spaces. Well, each of them has a dimension prescribed by E. So it's in Gr, EI, MI. Well, and since this is a sub-representation, they have to be such that whenever I have an arrow, again, A from I to J, well, then MA has to send NI to NJ. Well, in fact, this is clearly embedded in the product of Grassmannians, and this inclusion relations are closed. So in particular, this is equipped with a structure of complex projective algebraic variety again. Well, it is not, well, maybe it's nicer. I was about to say it is not as nice as the flag variety in the sense that it is in general singular. It might fail to be normal, but in fact, that's why probably it's more interesting. Okay, so it's richer. So now, so the first observation is that the notation, first of all, is compatible with the one we used above, because if we take a quiver with only one vertex and no arrows, well, then we really recover the usual Grassmannians. as above, ICN. But also, my point is that the flag variety word is the subword, if we want, of the Quiver-Grassmannian setting. So in the sense that we can realize FLN, well, afterwards I want to give another realization, but for the moment, let us look at the AN-1 equioriented type AN-1 quiver, and then consider its representation whose underlying vector spaces are all CN, and the maps are all the identity maps. Well, then if we look at a Grassmannian, where the dimension vector is 1, 2, and -1, well, this is, clearly isomorphic to FLN. Okay. So that's somehow the dictionary that we should have in mind. Okay, so whenever we would like to generalize something to the quiver case, if we want that it is really a nice generalization, in some sense, we do want that whenever we apply this theory to these representations, we recover what we know about FLN. So that's the first important thing to keep in mind. Okay, now we know what the varieties we are interested in are, somehow the families of varieties we would like to work with. But now remember the spaces we wanted to keep with a group action were cohomology spaces where there was some equivariant. So we talked about equivariant cohomology. So the next thing we have to do is to define torus actions. Well, so the action of the maximal torus of GLN in the flag variety case is very well known. So a way one can define it in a, let's say, more canonical way, just to say, well, GLN is just automorphisms of CN, and so there is an induced action of diagonal matrices within GLN. And here, this is so the action, the way I want to recall it is more explicit, if you want, in the sense that we do want to fix a basis. So in some sense, it's less canonical, but it's what we want to generalize afterwards. So we fix a basis of CN. And then, well, our torus is n copies of C star. And when we let it acting on CN, well, by saying that a tuple acting on EI, it rescales EI by the ith entry. And then we extend it by linearity. Well, in this way, we get first an action on CN. Well, and of course, again, that's nothing but an automorphism. So in particular, it preserves all dimensions and inclusions, and so it induces an action on FLN. Okay, so just a diagonal action, if you think of a flag as a collection of subspaces. So now the first trick, the first difficulty is to find a torus which acts on the Grassmannian, on the quiver Grassmannian. So we'll see that afterwards, if the action is nice enough, this is going to have very good consequences from the cohomological viewpoint. So that was something that Alex and I studied mainly last year. So that's I'm going to spend some time recalling what our previous results are. So in this case, we have to focus on specific quiver. So we look at the equioriented cycle. So let's say 1, 2, and so on, and -1, so an n vertices. Well, here maybe one can see, well, it's probably convenient to identify a representation with the pair. So first we have a Z monon Z graded C vector space. Okay, so well, what we are doing is just taking the direct sum of all these vector spaces we had before, and just remembering on which vertex it lives, each piece, its graded piece. Well, and then an endomorphism of this C vector space such that whenever I apply it to MI, well, its image is contained in MI plus 1. So here I and I plus 1, well, I plus 1 is considered mod n. Yeah, so if I apply phi to Mn, I want that its image is contained in M1. So it's convenient to give this description because what we want to do is now to restrict to a particular class of representations for the equivariant cycle, which are the nilpotent ones. And now it's easy just to define them as well. These are their nilpotents if and only if this endomorphism phi is itself nilpotent. Okay, so that's a matrix, so you want a nilpotent. So we restrict, maybe let me state it in red. The first, so we restrict to the case of M nilpotent, which means that the map phi is a nilpotent endomorphism of that vector space. Okay, so let me give a first example, which is going to be important. So for example, for any vertex of our delta n and any strictly positive number, we can consider the following delta n representation. So as we explained upstairs, so we need, first of all, a z-graded vector space. So let's say it's the span of L vectors. So this is L. Well, this is a vector space, so the span over C. Now it was Z mod n Z graded, so I have to declare some degree. Well, one. Yeah, whatever. So this degree is given in such a way that WL has degree I, and then L minus 1 is degree I minus 1, and so on, just wrapping around, if you want, this string around delta n. And then we can explicitly define our endomorphism by declaring WK being equal to WK plus 1 if k is less than L, and 0 if k is L. Okay, so this is clearly important. Okay, so it's just a matrix if you want with just ones just over the diagonal. And also it's not hard to say, so let me say this fact, that UIL is indecomposable. So what requires a little bit more work is that in fact every indecomposable nilpotent representation has this form. So meaning that as soon as I know that M is nilpotent and indecomposable, well, there exists I and L such that M is isomorphic to some IL. Why is this important? Well,
Martina,
yeah.
I'm sorry, in the definition of phi, I think
oh, sorry.
There's K should be L, right? So I mean, you're writing phi.
Yeah, absolutely. There's no K0. Yeah. Thank you, Evgen. Yeah, that's why I meant, so if we, so meaning that if we look at find the basis W1, WL, what we get is really just 0 here and then 1. So yeah, we are killing WL, as you've noticed. Okay, well, but then, so another important fact is that, well, as I said, I want to focus on the class of nilpotent representation. Well, the finite dimensional representations of Q, actually that's a Krug-Schmidt category. Well, meaning that if I can classify, as I said, all nilpotent indecomposable representations, whenever I have M, which is nilpotent, I know that it's going to decompose into direct sum of copies of UILs. So this is going to be some UIL with some multiplicities. So here we're varying I, and here we are varying L. Well, since we said our representations are finite dimensional, well, here there's going to be some N which bounds my direct sums. Okay, the length of my indecomposable pieces. Well, anyhow, I don't really want to focus on this N, but rather on the fact that, well, I do have some number of indecomposable summons. Can you still see what I'm?
Yes, I see it. Yeah.
Okay, because my laptop shows something weird. Okay.
No, so the last line is that M is isomorphic to the direct sum.
Yeah, I don't know what's going on. Okay, you tell me if there's something, because I cannot see anything anymore on my laptop.
Oh. Yeah,
So,
well,
whatever. Fingers crossed. So okay, so I just stated that I take a nilpotent representation and assume that I have the indecomposable sum. So now so remember that this UJ is going to be isomorphic to one of these UIL. So in particular, I have a distinguished basis of the underlying vector space, which has this form. Okay, so in this case, let's say this is.
Martina, did you write something or?
Yes.
So you wrote some vectors or? So what?
Yeah,
at the moment you can see this line with M isomorphic to direct sum and nothing else.
Okay, this is bad. Okay, give me 1 second.
Yeah, sure.
Sorry, there is some weird message. Stop screen mirroring. Okay. Maybe I stop to sharing and I start.
Stop sharing and then try again.
I'm sorry about that.
No, it's.
Yeah, I felt like that something weird was going on. It looks better now. I think it's okay now, right? Yes.
Right. Yes.
Okay. So I was just saying, well, so assume we do have D indecomposable summons. Well, we know that they are all isomorphic to some U, I don't know, I, J, L, J, okay, each of them. And so there is a distinguished basis for the underlying vector space, which I'm going to define W1J up to WLJ. And now we're ready to define the torus action. So this is maybe just a parallel with what we were doing with the fact variety case. Once again, so this is the analog of saying I fix a basis of Cn. Okay. And so now what I want to do is to define my torus. That's going to be 1 plus D copies. So D is the number of indecomposable summons of C star. So now let me first consider the underlying vector space to M. So that's a direct sum of all these vector spaces. Well, so first, I'll define a T action on V. And I just have that an element of T acts on one of the distinguished basis element WKJ via TJ, WKJ, T0 to the K. So whatever, let's say we somehow, what we're really doing is that we took these indecomposable summons, we number them, and then we keep track of which number my vector on which indecomposable summons my vector lies on. And then this K is telling me also which element of my ordered basis I am picking. So at which point on my distinguished basis the guy lives. So, so now a first observation is that, well, in fact, because of this T0K to the K, well, T is not really a subgroup of the automorphism group of M as a delta N representation. So if it were, somehow it would be, we would automatically get an action on the Quiver Grassmannian. Well, but still, it's an easy check that, well, this action, in fact, induces a T action on Giro EM. Okay, so maybe I haven't noticed that, of course. So Giro EM might also be empty, but we just assume that we pick a, like a nice dimension vector. Otherwise, also like all statements are empty. So a remark is that, in fact, from this construction, we just don't recover immediately the torus action we described before for the flag variety, in the sense that, so there is another way we can realize the flag variety before as a Quiver Grassmannian. So earlier I gave you a realization in terms of Quiver Grassmannian for representation of equivariant type AN-1. We said we want to deal with delta N, but somehow every representation of AN-1 equivariant is a trivially nilpotent representation of delta. So this can also be realized in our terminology as n copies of this irreducible, indecomposable nilpotent representations, UN-1 and -1. Well, so in this case, what we get, well, in fact, there is a subtorus of the torus we've just described, which is n-dimensional. So it sends the tuple T1, Tn to, and we get an embedding on the torus, which is 1 plus D, in this case, D is n-dimensional. And then in this way, we recover the usual torus action on FLN, which in this case, indeed, would also be a subgroup of the automorphism group of FLN as, oh, here, I didn't write it, 9. I mean, that's Gr 1 and -1 of this. So this extra dimension is not really useful in the flag variety case, but since we are dealing with delta N representations, which are in some cases related to the affine flag variety, the affine Grassmannian, it is actually natural to have an extra dimension. And it will be necessary in what we discuss next. So on my to-do list, I had now equivariant cohomology. So I'll step back a little bit and say something about a more general setting. So it will be enough for me to work with complex projective algebraic varieties. And actually, so we'll always be dealing with varieties whose odd cohomology vanishes. Well, and then we said we want to actually consider T varieties, so varieties equipped with an action of some algebraic torus, which is nice in the sense that we have only a finite number of T fixed points and a finite number of one-dimensional orbits. So whenever I have this package, so these three properties hold, I will refer to the pair XT as a GKM or GKM pair from Gorecki-Kotlitz. Also, under this hypothesis, what happens is that whenever we have a one-dimensional torus orbit, well, its closure is smooth. So it's isomorphic to a P1. So it's really just the union of O with two fixed points. Well, now Tx on this orbit. So on the orbit closure, we are going to have the fixed points plus the C star. Well, that's a C star. T is an algebraic torus. So it has to act on C star by a character. Okay, so T acts on O via character, well, which is uniquely determined by this isomorphism. So let me denote it alpha O, which is then, as I said, an element of the torus character lattice. So homomorphism of algebraic groups between T and C star. So now there is this dependence on the fixed isomorphism, but the only thing that it can change is a sign. And this you can already imagine it. Well, if you haven't seen that, I recommend you do it as an exercise for SL2 flag variety, so you get P1. And then the character of the torus is going to depend on the atlas you pick. So on the isomorphism, you really write down from P1 and C star. Okay. Well, from an open dense part of P1, you have to decide which isomorphism you pick. So this character is uniquely determined up the sign, and we'll see that it's not going to play any role. So that means that if we have a GKM pair, so a variety we equipped with a torus action with this nice property, well, then we can look at the one skeleton, and this draws a graph. Okay, so we pick just one-dimensional orbits. Every one-dimensional orbit in its closure has two fixed points. So we really get a graph, which is called the moment graph. And so a set of vertices, we said we had fixed points. Set of edges, these are unoriented. We have one-dimensional orbits. But in fact, we also want to label them. So every one-dimensional orbit or every edge is labeled by the corresponding torus character. So we send alpha to alpha O, and somehow we fixed. So we fix a sign once and for all. Okay, so for any edge, we pick one sign for this character. Okay, so why is this relevant to us? Well, because there is a theorem, well, which is nowadays known as GKM version of the localization theorem. Is actually in this form. I want to recall that is due to Chang Scalebread, because Gorecki-Kotlitz and McPherson discuss more general cohomology theories, but somehow nowadays this is known as GKM theory. So assume that XT is a GKM pair, and then denote by R the symmetric algebra of the C vector space spanned by the corresponding C vector space. Well then, so here I am, with complex coefficient. Somehow the same would work with Q. So here, that's isomorphic to a tuple of polynomials. Okay, so symmetric algebra is really just polynomials in number of variables, the rank of the torus, which coefficient the field you pick. And then, so we have this tuple, this bunch of polynomials, one for any vertex, which have to satisfy some Lewin conditions, which are dictated by the labels on the edges. So fx is equivalent to fy modulo alpha O whenever we have an orbit whose closure links x and y. So again, so if you haven't seen or you didn't or you don't remember what the definition of equivariant cohomology is, you can just take this as a definition. Let me maybe share it. Okay, so let me tell you what the moral of the story is of, let's say, this page. Okay, so let me, again, write down sort of a slogan. So the moral of the story is that if we have a torus acting nicely on the variety, well, then there is an associated graph, which is called the moment graph, which encodes T equivariant cohomology of X. Well, I mean, this sounds somehow it's really nice, but of course, this is going to be useful if we have some combinatorial control on the graph. Otherwise, it's not going to give us much more information than before. So that's so I think what I'm going to do now is to recall what in the flat variety case happens, and then we're going to see that in fact much of this can be extended to the quiver setting for delta m. So flat variety case. So remember, GKM means, first of all, we want that the variety X, well, for us in this case, has no cohomology in odd degrees. Well, but it is easy because FLN, well, has a cellularization, right? Or you can say it's a CW complex. So by supercells gives a cellularization of FLN, and so in particular, well, this has no odd cohomology. Well, and moreover, what do we know? Well, the fixed points of the torus section are nothing but coordinate flags. Okay, so remember we had fixed a basis, and so let's denote by E sigma k, the space generated by E sigma 1, E sigma k, and E dot sigma is the corresponding flag. So these are the fixed points. So in particular, they are in one-to-one correspondence with permutation. Well, as for the one-dimensional orbits, I'm going to skip the geometric description and just jump in the combinatorics. Here, the one-dimensional orbits corresponds to pair sigma ij sigma. So here, that's an undirected simple graph. So I just pick once sigma and ij sigma, where ij sigma is just less multiplication of sigma by the corresponding transposition. And here we also have a label function. Well, okay, so first let me notice that, so by this we have a finite number of fixed points and finite number of one-dimensional orbits. So we can declare that they are the vertex set and the edge set of the corresponding moment graph. And then we have a label function which sends a pair sigma ij sigma to the character of the torus epsilon I minus epsilon j, where epsilon k is the torus character sending T1 Tn to Tk. And here you notice that there is indeed some sign issue going on, because the transposition ij is the same as the transposition ji. So indeed, this is defined after sign. So let's say one just decides to pick what are just the positive roots. Okay. But again, remember that we care about these labels for this description of equivariant cohomology, and the condition mod alpha O is not affected by a sign. Okay. So it doesn't really matter if I write alpha O or any invertible, so any non-zero multiple of alpha O. Okay, so here we get this moment graph, which is somehow had appeared already in the literature, had been studied a lot, and it's also known with the name of Bruha graph. Maybe when one talk about Bruha graph, often also has an orientation of the edges, which we are forgetting for the moment. So let me give an example. So for example, for n equals 3, well, we have 6 permutations. Let me write it in, write them in the one-line notation. So these are our 6 fixed points. And now I want to remember which ones are connected by a transposition on the left. So it's easy to see that these 3, this red edge corresponds to left multiplication by transposition 1, 2. Then this blue edge corresponds to left multiplication by transposition 2, 3. And then finally, the vertical yellow or orange one corresponds to multiplication by transposition by 1, 3. Okay. And so Goreski, Katwicz, McPherson description is telling us that, for example, the following is an element of the T equivariant cohomology of FLP. So let's say I want to start with 0. Then here, corresponding to this entry, I'm going to need a polynomial in epsilon 1, epsilon 2, epsilon 3, which is congruent to 0 modulo 1, 2. Okay, so for example, epsilon 1 minus epsilon 2. Let's say I want to put here 0 again. And here I want a polynomial which is congruent to 0 mod red, which is epsilon 1 minus epsilon 2. And here has some congruence condition, but since the two are equals, I have no problems. Well, and I'll complete it this way, and this is the unique, that's the unique element having such in this way. I can complete it only in this way. Anyhow, so you can check, exercise that this is indeed an element of the ring we've described before. Yeah, so you have a very explicit description of the elements of the equivariant cohomology. Okay, so what can we do in the Quiver-Grassmannian case? So again, remember with restricted to the case of nilpotent representation of the equioriented cycle. So what we proved with Alex last year is that our torus action I described for you before is provides the Quiver-Grassmannian for M of a GKM variety structure. So what we can get, in fact, is combinatorial description of the underlying moment graph. So I decided I'm gonna actually say something about it. since so my point before was that somehow just to prove that something is a GKM variety is a bit pointless if you don't get a good control of the combinatorics of the graph. And in fact, that's really this great control we had that allows us to prove what we have for representation, for permutation representations. So pick our M. And now we pick, again, a basis of the underlying vector space. So as before, we had this collection of WIs, L, J, J. Where J here again varies in the number between indecomposable segments. So what one can do is consider another quiver, which is called the coefficient quiver, which is defined as follows. So first of all, the vertices, well, are exactly the vectors in the basis, and then the edges, well, the errors are given by WKJ, WK plus 1J, where J is one of our indecomposable, and here these are just, well, these errors corresponds to the maps phi. So we just let K vary from 1, well, J minus 1. So in fact, one can recover the representation from the coefficient quiver. Oh, maybe I wrote a little too big. Let me just move this tiny bit up and rescale it a little bit. Okay. So, so for example, if you look at one of our indecomposable nilpotent guys, well, we said already B in this case is 1 WL. I drop the index, the upper index 1. And in this case, the coefficient quiver is just going to be some type AL AP-oriented quiver. So now lemma tells us that, well, maybe let me just write X for our quiver Grassmannian. Well, then the T-fixed points are in one-to-one correspondence with what are called successor closed subquivers of the coefficient quiver of dimension vector E. Okay, so where this set is nothing but the set of certain subquivers of QM. So let me write full in the sense that they are uniquely determined by the set of vertices which are which belongs to them. So first of all, I want that the cardinality of the vertex set of this subquiver, well, when I look at the ones, or maybe let me see this. So I have my basis, and then I want to remember that this is in Z graded. So I can rearrange all my basis vectors according to the space Mi they belong to. So that's the basis for Mi. And so here one that I have in Q0 bar exactly EI elements of degree I. And then whenever I have a vertex in Q0 bar and an edge from B to U in QM, well, also U is in Q0 bar. So intuitively, this is exactly what the name says. So I pick whatever sub quiver I like with this prescribed number of vertices over any of a given degree, but in such a way that whenever I have a vertex, I also have all the vertices which flows from it, so such that they're connected to it toward via an oriented path. So for example, let me quickly look at this example. So if we look at QM like this, so we look at this representation whose the quiver Grassmannian of dimension 1 and on dimension vector 1, 2 gives us the usual flag variety in C3. Well, then so I said E1, 2. So what's the successor of subquiver of dimension vector 1 and 2? Well, I have to pick one element over one. And then I'm forced to take this because that's an arrow, and then I can pick either this or this. And then if I start with this, I'm forced with that, and I can take either this or this, and so on. So if I start with this, I'm forced with that, I can take either this or this. And now it's immediate to see that here we have a one-to-one correspondence with permutations in S3. And it's an exercise to show that it is always the case. So for the moment graph, we also needed to say something about the one-dimensional orbits. So these are now in one-to-one correspondence with pairs of successor closed subquivers of the prescribed dimension vector. Well, such that, but what I can do now is to compare these subquivers, and in particular, remove from one the intersection with the other. And I want to get something which is predecessor close. Now, I mean, this should be clear what by predecessor close what we mean. It's somehow the notion, the dual notion to successor close with just discussed. So that's the predecessor close, a connected subquiver of QM. Well, this really means that this is nothing but some segment, so some oriented type A something. So this is going to be W1J for some J, W1, W. KJ. Okay, so it's a piece of one of these guys. And the same.
I'm sorry. Is there any connection between L and L prime?
Yes, this is what I'm explaining. So here I'm saying when we want to have when we're going to have a one-dimensional orbit.
Oh, I see.
Yeah.
Okay.
What we do is that we pick two successor closed subquivers, and then in some sense we are comparing them.
Yeah, I see.
So I remove from one the vertices which belong also to the other one, and I'm saying that they're connected if and only if when I do this procedure to both, I only get some predecessor close connected subquiver. And here, so I'm just going to copy what I had before, but I had to exchange the role of L and L prime. And here I'll have some other index. So I, J, H, no, that's an I. So, and here one can also explicitly give the label, which is going to be epsilon I minus epsilon J plus H minus K epsilon 0. So let me say something. So again, here, this I, J, K, H depends on this vertex here. And once again, I have to decide which one is stronger, which one I prefer. So before we had this epsilon I minus epsilon J would have been the same to take epsilon J minus epsilon I, and here I'm doing the same. And decided that I'm taking this and subtracting this way. And again, I'm using the same notation as before. So epsilon S is the character of the torus sending T0, TD to TS. So epsilon 0 is the one corresponding to T0. So whatever, it is a bit involved, but there is actually a very neat combinatorics once you get used to it. And the exercise is that for m equals u n minus 1 tensor Tn, and E equals 1 to n minus 1, well, you recover the Bruja graph. Okay. All right. So we are finally there. We're finally able to define the symmetric group action. So I start by recalling Timotsko's approach. But let me mention that from a purely geometric viewpoint, there was already previous work by Brion. So, but for us, since I haven't said really anything about the Borel construction of equivariant cohomology of FLN, I just want to work with the localization, with localized classes. So for us, again, an element of the equivariant cohomology FLN is this couple of polynomials indexed by permutations. Okay, so remember that so F tau is in R, and R in this case can be identified with polynomials in epsilon1, epsilon n. And well, of course, we also have an SN action of R just by permuting variables. So that's also going to appear. So let's see. Let's define an SN action. So I define every element. So let's sigma be a permutation, and let's F be this tuple of polynomials subjected to the conditions we said before. Well, then S dot F is some other tuple, some other tuple of polynomials where F2 prime, well, is obtained firstly by taking the sigma minus 1, 2 entry, and then by twisting it by sigma. Where twisting it, I really mean by this action of SN on the polynomial. So, and Timotsko proves, well, let me just say it this way. In fact, well, let me just say this is a well-defined action. So she proves a little more. So she starts with a geometric action. She shows that's really the localization of this action. So for example, if we apply our transposition, well, the transposition 1, 2 to the class we had before. So let's see what happens. So well, first of all, we're gonna multiply every element by the inverse of 1, 2, but it's an involution, so it's 1 to itself. And so one multiplication by 1, 2 on the left was exchanging these pairs. Okay. So here I'm gonna get, well, 0 is easy. Here on the bottom, I get epsilon 1 minus epsilon 2, and then I have to apply 1, 2. So I exchange epsilon 1 with epsilon 2. And here I do the same. And now the last pair, I should exchange them, but they are the same element. And then I have to apply 1, 2 to the variables. So here I get epsilon 2 minus epsilon 3 and epsilon 2 minus epsilon 3. And then you can, just verify, for example, that these two are congruent modulo epsilon 1 minus epsilon 3. So this is somehow what one can generalize. So I'm going to tell you how to generalize this to our setting. So this can be probably generalized for a wider class of representations, but somehow since we want to deal with equivariant cohomology and still don't have a very nicely defined torus action on a bigger class of bigger representation, so I stick to our case. So remember our M was nilpotent and direct sum of the many indecomposable sums. And now assume that we have D bar, different isoclasses. And so that I can rearrange my indecomposable summands, like put in first O1 isoclass and then the second isoclass and so on. So meaning that I have U1 isomorphic to U2, isomorphic to UK1, and then UK1 plus 1 isomorphic to UK1 plus 2, isomorphic to UK1 plus K2, and so on. So now what I want to do is to consider the group which I denote SK lower bar, which is a subgroup of SD. So D again is the number of indecomposable summands, which is defined as the stabilizer of the following sets. So K1, K1 plus K1, K1 plus K2, and so on. Okay, so I should imagine that what this Kn is doing, what this SK underline is doing is acting on any block of isomorphic indecomposable summands. Okay, and so up to K1 plus K D bar minus 1 plus 1 up to D. Okay. In particular, what I can do is to define an action sigma.
Martina, do you understand correctly that this SK is a product of several symmetric groups?
Yeah, exactly. Sorry. Yeah, here is isomorphic to the product of all. Yeah. So sigma K is isomorphic to the product of all the sigma K1, sigma K2, up to symmetric group KD bar. Yeah, so indeed, maybe before defining it, I just have to be fair. So to stress the fact that if you pick like a random point in the representation variety of delta n, well, this group is going to be trivial in the sense that, so a generic point has all different indecomposable summands. But if there's a wide class of points in the representation variety having nice symmetric group actions. So think about the flag variety where all indecomposable summands are isomorphic. Well, that's what we want to generalize, and there's plenty of interesting representation having isomorphic indecomposable summands. Well, you can imagine the way the action is going to be defined. So first, we define it on the basis vectors. So we just say that sigma of what we call WKJ, well, it's nothing but WK sigma J. So we move these segments like all together. So we exchange the segment accordingly to the numbering of the vectors. So what happens is that sigma K, well, this product of symmetric groups sends successor closed subquivers of QM to successor closed subquivers of QM. Well, meaning that, so we have an action on the fixed point set, and now we can just define the action in the same way as Timosco did. Well, in fact, again, we can prove that it comes from a geometric action. This SK normalizes, in some sense, our torus action. And so, well, you can make it very precise. You can show that this action comes from a localization of a geometric group action. But anyway, we are just discussing here the algebraic definitions, and there is a well-defined action, which is given by what we said. It's exactly the same. So sigma acting on F is the collection of F prime L, where L is a fixed point set, which in this case is a sector cross subquiver of a right dimension. X is our quiver Grassmannian, and where F prime L is nothing but, well, I act by sigma to the -1. I look at the corresponding fixed point, and then I twist again this polynomial. Okay, that's exactly the same definition as before. Okay, so this is valid in very, 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 very great generality. So the generality we've so now what I want to say is something about the structure of this permutation representation. And there we're going to need to restrict to a certain class of quiver representation. But let me first recall.
Tina, can I ask a question?
Yeah,
So,
sure.
is it important that you are considering the loop quiver, but not the equioriented, say, type A quiver? So either.
So the equioriented type A quiver is somehow a subcase. So you yeah, because you can see every finite dimensional representation of type AN as a nilpotent representation of delta n.
I see.
It's just the last arrow is 0. So
I
you're sort of opening up the delta n. So it's generalizing the type A.
But vice versa, is it true that if you consider the loop quiver, then it's equivalent to considering some very large type AN equioriented?
I don't know, but how can you get the condition between n and 1? I'm not sure. Somehow you need some extra, right? So, I mean, if the support is small, then you can probably do it. But otherwise, you live in a bigger space because you have this extra arrow, which is which is imposing you something else.
Okay, thank you.
Yeah, so it's wider, at least. Yeah, otherwise the two representation categories would be equivalent, which is not the case.
So just what I'm thinking about is that if you have a kind of a very long
type AN
of a loop quiver, you can somehow unloop it, considering as a kind of
but then you still, I don't know.
Okay, anyway,
I don't know. Yeah, maybe you're right that if so you take the important parameter if it is finite dimensional, but I'm worried that you still have somehow conditions on the fact that, I mean, some vector spaces have to be the same.
Yeah, okay.
I don't know. No, but maybe you're right.
No, just forget. Yeah. Please.
No, we should think about it actually. Yeah. So so I wanted to say something about the representation structure, and there was something that Timotko proved in paper appeared on GEMS. So the theorem is that somehow this representation is very boring. So I can state it in better terms. So what she proved is that the SN representation HT flag n. Well, I write something and then I'm gonna explain what I mean by this. So this is direct sum triv. Let me say so triv is in sigma is nothing but as an R module is isomorphic to R, all concentrated in degree twice in sigma, and im sigma is the number of inversions of the permutation sigma. So let me say, is isomorphic as what? Well, as a graded twisted R module. But here, this is fundamental because of course it's not just acting trivially everywhere, but you are twisting the structure of the cohomology at the point the way we said before. So in this meaning that sigma, well, is what we said before. So sigma of G epsilon 1 epsilon n is G of epsilon sigma 1. So surprisingly, we could, under, well, technical assumptions, which I don't want to recall, but, well, the same holds. Well, I have to somehow make sense of inversions. So I decided to state it this way. So there exists an orientation of the edges of the underlying moment graph. So remember, X is our quiver Grassmannian for an important representation. T is the torus as defined before, of the edges of the underlying moment graph. So such that, well, somehow the same as before holds. So I'll just copy the SK underline representation, HTX is isomorphic. Well, that's the direct sum on the fixed point set. Here we have some twisted R modules in the sense I've explained before, but I have to tell you with IMV of a successor closed subquiver is, well, this IMV really depends on the orientation. So let me try to explain what I said, because this sounds really as a very technical and empty statement. So the idea is this. So we have this moment graph arising as if you want, a one skeleton of a torus action on a variety. So now, in fact, there is a geometric way of orientating the edges, which I didn't discuss, which depends on some torus co-character. Okay, so you are, in some sense, again, it's a little bit about the sign choice. So you are deciding where is the zero and where is the infinity of your P1. Okay, so that's well, a precise way of explaining this in terms of co-character of the torus. And so once you get a correct, so a nice orientation of the graph, then you can look at this set. So this set is the set of arrows starting from a given edge, is the set of arrows starting from a given vertex, and then you count them. So this is exactly what inversions are in the case of Sn, in the sense that this has something to do also with the dimension of the corresponding Schubert cell for the flag variety. And here you can also rephrase it in the dimension of a certain cell in a cellular decomposition for the quiver Grassmannian, which I haven't discussed. Okay. But anyway, there's a way of getting exactly the same result for quiver Grassmannian. I have to say that these technical assumptions for the moment are restrictive, so they're not completely easy to verify. So that's a big class of varieties satisfying them. Of course, you recover all partial flag varieties. You recover some finite dimensional approximation of the affine Grassmannian of the affine flags, some degenerations of them.
Martina, and these are assumptions on M or on what?
These are assumptions on M.
And also on the dimension vector or on M?
No, actually not. These are about somehow, so everything depends on the fact that your coefficient, well, around the coefficient quiver on M. So if you can rearrange the segments of the coefficient quiver in a nice way.
Okay.
So that's something that you also need, for example, to prove that this variety is GKM. But in that case, you prove that you can always rearrange the coefficient quiver the way you want for delta n. But in this case, you need also some extra assumptions, which are not trivial at all. So you still have a big family, but it's not as satisfactory as that. On the other hand, it makes sense because it would be very boring if you always had only the trivial representation. So here, that's a lot of things. I mean, that's a lot to do, I would say.
But do you have an example where this representation is not trivial?
I mean, we've been really focusing first on this because we needed to have a very good understanding of the combinatorics of the graph. But you have a sort of like, yeah, this inversion, so that the combinatorics of the inversions, or if you want, the positive roots and negative ones, so you recover all of this.
Okay.
So we spent a lot of time on that, and we didn't manage to look at other cases yet. So maybe I still have 5 minutes. And I'd like to mention that there was something about the Neal-Hecke action. So, yeah, so just let me recall, or let me define for you if you haven't seen this. So we are interested now first in the morphisms of polynomial ring with n variables, which I keep denoting by epsilon I for obvious reasons. And here I want to look at partial j, where j now is at most n minus 1. And this is what's known with the name of divided difference operator or de Mazur operator, or BGG operator. So this is just, I take a polynomial g, I subtract, well, g after I have acted on it via the transposition j plus 1, and then I divide it by epsilon j plus 1 minus epsilon j. So this is again an element, a polynomial, and so it is an endomorphism of that ring. So now what we look at is that the Neal-Hecke algebra, well, H0n, which is a subalgebra of this endomorphism ring generated by the partial j's. Okay, well, this has also like well, just a generator and relation presentation. So you just take all your delta j as an algebra generators, and you quotient by delta j square equals 0, and then the braid relations. We have delta j, delta I, partial j, partial I for j minus I greater than 1, and then partial j, j plus 1 j, it's the same as partial j plus 1 j, j plus 1. And that's why it's called Neal-Hecke. So it's a sort of relations for the Hecke algebra, but when you take the generator, you squared, you get 0. And so in the flat variety case, that's really so all work of Kost and Kumar in way greater generality. So they were working with generalized flat variety for category groups. Well, they've defined the analog for the equivalent cohomology. So let me say you define DJF as F minus again J plus 1 F, in the sense now we are thinking of it in localization terms, so localized terms. So this is again an element of HT of FLN. And so now what one has is that there is a faithful representation. So we have a Z-graded.
Martina, I'm sorry, do you mean that F is a collection of polynomials, right?
Yeah, F is a collection of polynomials as before, and this is the action we defined before. That's why I'm saying I'm rephrasing Kost and Kumar, but they already have everything localized, even if they didn't realize it was exactly isomorphic. So there's some ring they call lambda, and that's exactly our HT-FLN.
Okay.
Yeah. So yeah, you should think this this is exactly a simple transposition acting on our tuple of polynomials that we said before. And it's an easy check to see that, in fact, you get that this difference is a tuple of polynomials, all multiples of epsilon j plus 1 minus epsilon j. And so you can divide and what you get again verifies all the conditions in JKM theory. So this is Z-graded ring homomorphism. Z-graded ring homomorphism. And in fact, as I was saying, so Z-graded, well, I haven't talked about grading, but this delta J, so here, since we are seeing our variables as in cohomological degree, they all have degree 2. So delta J as an endomorphism of a graded ring has degree -2. And here again, delta J for the same. So here really we have the gradient coming from the cohomology degree. This is again degree -2. And so this is this Z gradient I'm referring to. So in the Quiver-Grassmannian case, well, again, so here we don't need any technical assumptions at all. So the usual setting, so M is nilpotent, finite dimensional. And then here we look at the sub algebra generated by the partial J's, where J plus 1 is in our Coxeter group. Okay, so that's again a sub algebra, what we've denoted upstairs H0D. Another theorem is that we have a Z-graded ring homomorphism. So here, here is GREM. So that's a Z-graded ring homomorphism. So here, in fact, we do see differences with the classical setting, in the sense that while the homomorphism in the flat variety case is injective, so one gets a faithful representation, this is not the case in general here. So it would be, of course, interesting to understand whether one can give conditions for faithfulness. Also, so was fundamental in the work of Costa and Kuma that HTFLN was a cyclic module for the action of the Nil-Haeckel, because that's the way, for example, one constructs equivariant Schubert classes. This is not the case for the Quiver-Grassmannians. Again, well, in general, of course, in the flag variety case, you will recover the same result. So it would be, for example, interesting to understand whether one can give condition about cyclicity. I think, well, I'm a little over time. Yeah.
Yeah, may I ask a question? So what is the essence of this statement that this is ring homomorphism? So there is a multiplication in the Nil-Haeckel algebra, right? And then
yeah, exactly. So you can, maybe I should have said. So the way you prove it is that you just, there is I should have just said that you take your partial J, you send it to DJ. And you realize, you verify that the DJs verify the same defining relations.
Yeah, but they're given by the same formula. I mean, what is the what's the problem here?
No, I mean, a priori, so okay. So here, this is, well, of course, so this is, I mean, they are given by the same formula, but a priori, so if you were working with a bigger ring, you wouldn't know that you would stay inside. So you see, you have to give away something. So this is, let's see, okay, this is a for free statement from the classical setting plus what we constructed before. Yeah,
yeah, but even in the constant Kummer situation, so I don't understand.
Because it's not clear. No, a priori, I mean, these are, you see, so this is a statement at the, at the level of polynomial ring.
Yes.
And this is a statement at the level of tuples.
But do you understand correctly that so for at each, so F is a collection of polynomials, right? And on each polynomial, the action is given by the same formula.
Yeah, I mean, a priori, you could have more relations, right? So here, the surprising thing is that you don't have more relations than that.
But you are saying this ring homomorphism, not. So I mean, it means that the relations on the left should be satisfied on the right. Is it correct?
Yeah.
But then you are kind of, it's just enough to check that all the relations from the left hand side are satisfied on the right hand side. But so I just don't, what I don't.
I mean, yeah. I don't think so. Yeah, maybe what's the delicate thing is this. Yeah, let's say there is a ring homomorphism, and that you can really define this way. So you have to do some computations here. It does not come just straightforward. So you have to verify that you're still here.
So what I don't understand is why. So suppose we checked it in one point, yeah. So just at one t-fixed point. So why we don't get the whole result from this? So why the action just at one point?
No, because it is not so a priori. So what's not clear is that the I is well defined. Because you have so you define the I if you want from the direct sum of copies of R's.
Right.
Let me say like this.
Uh-huh.
Whatever your setting is.
Uh-huh.
So this is, of course, well, that's also a priori not well defined, but you notice that whatever you're applying a simple transposition, so the way the symmetric group is acting, in fact, you go from R to R. Mm-hmm. What's not clear is that, so when you apply the I to mm-hmm. F, mm-hmm. and you look, let's say, at the, I don't know, the X component, mm-hmm. then this is not clear a priori.
Oh, I see. Yeah. Mm-hmm. Mm-hmm.
Yeah. So I haven't. So the fact that the isomorphism is explicitly given by these DIs has to be checked. It has to be checked that it is well defined, mm-hmm. so that all relations are still valid. And so a priori, yeah. So you have to check something.
I see.
It's an easy. So it's not. But it a priori it's not clear.
I see.
Yeah. Now so one gets a representation structure also with respect to this Nil-Hecke ring, and so which is somehow very different from, or somehow different from what happens in the classical setting. So I think it might be worth it to be investigated. Also, I mean, for example, well, okay, I don't want to keep talking, otherwise it's too late. So that's, for the moment, that's all I wanted to say. Thanks a lot.
Thank you very much. So are there any questions? So actually, I have a couple of questions. So first of all, what is the connection between the action of the symmetric group of Timoshko action and the action of this Nil-Hecke algebra? So are they somehow related?
Yeah, I mean, so that's so you're using this. This is so that's the action.
Ah, this is exactly the action.
Yeah, exactly. Sorry, no, that was exactly the point.
Oh, I see.
Yeah, that's exactly the point. That's why it's it's more delicate than what one thinks. Mm-hmm. Yeah, in fact, that's also the other. So the right action, which one can define more easily in the sense that you don't need this extra twist, and that's what I mean. That's what really appears in constant Quiver. That's I mean, that's not that different, but one should be. So for example, if you just look at the representation, at the permutation representation appearing, this is not a trivial one. And that's something that it's, I started thinking about it, whether one could try to generalize this. But for example, it's not clear how to generalize this even for partial flags. But, yeah.
Okay, and the second question, so do I understand correctly that if you take a quiver Grassmannian, then this equivariant cohomology, they form an algebra, right? I mean, with respect to the pointwise multiplication.
Yeah.
That's true. And do you have any control on this algebra? So is there a way to describe it?
Yeah, so
what's the dimension of this algebra, or I don't know?
Oh, as an R module, you mean?
Yes.
Oh, no, as an R module, it's so since we can prove that it's GKM, so it follows from GKM theory that it has dimension the number of fixed points.
So for any quiver Grassmannians, it doesn't depend on that, right?
Well, for the quiver Grassmannians, we can prove that they are GKM.
So for any GKM, it works, right?
Yeah.
Oh,
yeah, because so as soon as you have vanishing of odd cohomology plus finite number of fixed points of one-dimensional orbits, you can somehow see that you recover the usual cohomology just by, so this cohomology is a free module over the cohomology of the point, and then the number of generators is really the number of cells.
I see.
Yeah. And in fact, under the technical assumptions I didn't want to state, you can find exactly the analog of the Schubert basis. So in our previous paper, we had a more general basis, which you can always construct by using the singularizations, for example. And in this case, you don't need the singularizations, they're way nicer. They have sort of what Timosko calls Knudson-Tau classes or flow-up classes, and you can control everything. So it's really pretty. So for example, yeah, I don't know, my hope is that one can get some control in certain cases about structure constants, like sort of Pieri rules. So for specific pairs of classes.
And these flow-up classes, you just fix some vertex, and then you go by along the arrows, keeping the same element there, right?
Yeah, so it's what I was, my example in FL3 was one example. So when I said there is a nice orientation of the edges, was exactly because the idea is that you orientate the edges in such a way that when you pick your favorite vertex, that you put the product of the edges going down here, then 0 on all non-comparable vertices, meaning that you cannot reach from this guy the other vertex. And then once you have this, you can extend it in a unique way.
I see.
Yeah, and this gives you a great control. And so somehow by using this, we can prove this triviality statement. And then also you get also a side result, which is actually pretty strong. So that as soon as you have a cell, which is union, whose closure is a union of other cells, all results extend also to the closure of that cell. So for example, we don't have a geometric action on the Schubert variety, but you get an algebraic action on it.
Okay.
And you can prove exactly the same. And this uses very much the fact that these Knudson-Tau classes have a support that you can control that's compatible with the cellular structure.
Okay. Thank you. So further questions?
Yeah.
Okay. If not, Martina, thank you very much. It was very interesting.
It's a pleasure.
Thank you.
Grazie.
Yeah.
Let me
Now stop the recording.
share. Yeah.